Okay, I heard the blip. We're officially recording now. Okay, my students are like, yep, Warren, you do that all the time. All the time. All right, thank you, Melanie. So now, welcome to the History of Pi talk with me, Professor Warren Sides. As I said, I'm a mathematician / lifelong learner. History is a side note that I am just slowly falling in love with. For those of us who are here for a talk about pi, please be aware, this is pi, 3.14 blah, 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 and it keeps going, but we stopped. Not so much this. Okay, so even though there is pi in the back of the room right now, everybody draw your attention to the pi in the back of the room. There it is. Thank you so much. This is not what we're talking about. Okay, so pi, not pi. What is it? All right, so I'm going to start with what pi actually is, and this is very generic, this idea, right? And a couple of things, and I'm going to use the symbol for pi throughout, even though that symbol really didn't come around to like the 1700s, but we know it as the symbol for pi, it's the Greek letter p. So what is pi? Well, starting out, the circumference of a circle, okay, so we have this circle, the circumference is the length around it. This should be pretty familiar to most of you, hopefully all of you. The diameter is the length across, right? So through the center, there's the diameter. And you're not going to see a lot of the radius for us, but I will at least point it out there that the radius is just half that diameter. And I said this to someone before, and they were amazed by it, so I'm going to write it here. And all points on a circle radiate from the center, hence why they are called radii. Thank you. I'll be here all night. All right, so they radiate from the center, and the distance from the center to the, that's how far they radiate. So that's the radius. Thank you. Okay. And so what we're actually looking at here is it turns out that the ratio of the circumference, so the distance around, when you compare it to the distance across, is constant. It's the same for every single circle. And I think that was one of the cool motivations for people when they started getting abstract. It's like, well, that's weird. It doesn't matter how big or small the circle is, there's always this ratio that's true, right? It's the same motivation that people had for trigonometry when they started to notice that there's ratios to sides of triangles that were always the same regardless of the triangle. Right? The size of the triangle didn't matter. The ratio stayed the same. That's where the sine, cosine, and tangent. That's why we call them trig ratios, by the way, because they're ratios of sides of triangles. Right? So that same motivation here of trying to find this relationship between parts of a shape. And circles are a perfect form. So that's something that was really driving this here. Right? So that ratio, that constant ratio, that's pi. That's what it is. So throughout history, we're trying to seek the relationship between the distance around a circle and the distance across the circle. So as you see throughout, I'm going to switch. I'll start out by just saying the ratio of C to D, so the circumference to the diameter, and then eventually we'll start calling it pi, right? But our starting point is, how do we figure out this ratio? How do we determine how much around to how much across, right? And I also did put in some formula. This is the formula that we have for the circumference. Most people know it as 2 pi r, but pi times the diameter. And notice it just comes as that fact. If we know that the ratio is constant, then we can come up with a formula for the area or the circumference around a circle, right? The birth of pi. I like to start with why, right? I won't get into some weird analogy, but like, why are things born? Why do we have this motivation for it? And there's a couple of reasons. I don't know. I wasn't around 4,000 years ago when people started really thinking about pi, but I would assume they had some motivations, most of which were probably agricultural or some sort of wealth. I won't say money because it was a different concept then, right? So what possible motivation does one have to calculate pi, right? Why would you want to actually get to the point where you're calculating this number? What is this ratio, okay? So you might want to measure the boundary of a land, right? You have a circular region, all right? And you're trying to measure the perimeter around it. This is good for putting fencing up, right? You want to figure out how the boundary is. Now, I will point out, it could have just been, just measure it, right? Make a circle and then just walk around, right? Back and get your rope of a certain length and lay it out, right? You have it. There's no reason to do any of this stuff. But it does go further, right? Once you have that circumference and an idea of the relationship between the diameter and its circumference, you can start building on the area, right? The area is going to be a much harder thing to find if you don't know how the parts of the shape are related. Think of a square, right? The area of a square is really easy to find when you know the length of a side. Well, it might be helpful to find the area of a circle if you know the relationship between the diameter and its circumference. Right, so we're building this up. And I will, like I said here, land tax. In Egypt, there was taxes, things that got paid, right? So that was important to pay. Apportionment of land, either for inheritance purposes. Someone passes away and their land has to go to various members of the family. They have to figure out how to divvy that up. So they didn't know how big the area is in the first place before they can divide it up amongst the people that are going to get it. There's also sort of this idea of religious reasons. There's often very strict directions for how you sort of worship. And in sort of, actually in a lot of like sort of Hindu texts, circular altars, circular things need to be made, and they had to be made by very specific rules. And if you don't know the rules for creating a circle, if you don't know the relationship between all the parts, it's going to be really hard to worship in the appropriate way, right? So there's religious reasons for that. Astronomy was another big thing. People very early on realized that things were moving in sort of weird curved patterns, so maybe circular paths of celestial bodies. They realized that working on spheres was a big deal, so spheres similar to circles, so understanding that nature. I love this example, feeding domesticated animals. It's not quite as old as I would like it to be, but there's a grazing problem. If you have a goat hit a circular field, how long do you have to tie the rope up so they eat a certain amount of the field, right? Because you're trying to make sure they don't eat the whole thing. There's my fun picture of that. You can imagine the opposite situation where it's actually tethered to the middle, right? And then you're thinking, well, it's going to create a circle because they can only go so far from its rope, right? So what is that area that it's going to cover, right? How would I know that? How would I figure that out, right? And I always, now whenever I think of a circle, I think of a goat tied to a pin eating grass, right? But again, that was a big deal. How do we figure this out? How do I know I have enough to feed my goats? And then finally, I throw this in there because I think it happens at some point, understanding a mysterious relationship. It might have been motivated by practical purposes, land usage, money, animals, religion, astronomy. But at some point it was like, no, this is just weird, right? And now I feel like I have to figure this out. I have to know what pi is because we've been working on it for so long for our practical purposes, and it got to this really abstract place. So you're going to notice a little bit of the themes as I go through this. It's going to start very concrete. This is what it is. Here's how we do it. And then it's going to move into more of the theoretical. And then the shapes and the geometry pull away, and then it's all numbers and letters and weird stuff. I promise you, as the presentation goes on, I'll stop looking at the math too deeply after the practical stuff, and we'll just mention some of the evolution. Right? So we'll keep it light. So let's start with the early years. Right? Pi is born. Here it is, some 4,000 years ago in ancient Mesopotamia. So this is the Fertile Crescent between the Tigris and the Euphrates in the Middle East. Sometime between 1900 and 1680 BCE, we have all of these awesome cuneiform tablets. I imagine it's like at the end of the school year, all the students grabbed their clay tablets and just threw them in a pile, right? So all their math work is sitting there. For us, thousands of years later, they're like, oh, look at this cool math thing that they did, right? They're etching with their little cuneiform chisels and they're putting numbers together. Base 60, by the way, was their number system. Very complicated thing. No zero, no place values. So if you put a 3 on there, is it a 3? Is it 3? Was it 3 sixes? Is it 336? Is it 3 whatever? You don't know. It's all by the context. So you can imagine the hard work that archaeologists had when they look at something like this tablet up here, and they're like, okay, there's a circle, and these are apparently numbers. All these little scratches are numbers. Numbers base 60, right? So they have to figure that out, right? I'm laughing inside because I have students in my history of math class that are like, yeah, he totally made us do that. I made them look at Babylonian tablets and figure out what number is this? And by the way, there are 16 different answers because who knows, right? Based on the context. Anyway, so in this time, the ancient Babylonians used a ratio of 3. They said, when you make a circle and you cut the diagonal across, you can basically take that diameter and repeat it 3 times to create the circle. I often, again, just to give you an idea of what I'm thinking, I'm imagining actual people in a field, someone standing there with a rope and the other person's walking around them. Once they've completed that, they then take that rope and try to measure how many times they need to go around the circle they just made to figure out how many of those lengths of rope actually go around. They said about 3. Okay. I mean, we're at like 3.141592 something or other. That's pretty close. 4,000 years ago, that's really close. Right? They didn't have numbers like we did. They're doing base 60. They're doing no theoretical math whatsoever. They're just drawing things and hoping. All right? So that's a pretty good estimate. And I'm going to pause for a second here because this is where I have my activity. This is where I switch to showing you the pretty things that I want to show you and working on stuff. So while we're getting set up here, so people in the class, people in the room, people in this presentation hall, in front of you there's a piece of paper and there's a bag that has 2 pencils and a piece of paper with holes in it. For those of you who are remote, I'm sorry. If you have a compass and or straight edge, you might want to find one. Otherwise, you can poke some holes in a piece of paper and grab 2 pencils. Admittedly, the cardstock's not as nice as I would like, so it might be hard to make a straight edge on the edge of this. But the point is, if you pick one of the dots as your center and the other one as the radius, you can make circles with this piece of paper. Once you make those circles, I will show you why pi has been 3 in antiquity. Ready for this? All right, let me switch gears ever so slightly. I hope everybody's doing okay remotely and can see my new screen here. I also have to sit down for this one. All right. Boys ready for some fun drawing? Yeah, you are. People in the back, if you want, you can grab some too. I know you're eating, but you're good. Cool. And because I didn't want anybody to flounder alone, I'm going to do this with my crappy paper and pencil. Okay? So it's up to you, whatever size you want. I'm going to pick this as my center. So now I put it, I'm going to actually move it here. There's my center. And let's see, I'm going to go to the 3rd dot. Doesn't really matter. And I'm going to to the best of my ability, keeping my pencil straight, just move it around. There's your circle. And this is where I fall apart because it's not easy. By the way, at least in ancient Greece, they had much better compasses and straight edges. So their work probably looked a lot better than that, but close enough. You get a good one? Awesome, we got some people with good ones in the classroom. So I keep saying classroom, you know where we're at. All right, keep working on it, it's okay. But look here, I lost my spot. Here's this. So now I'm in the center and at the thing. So what I'm actually gonna do is going to be very complicated to show, and I'm sorry for that. I wanna walk it around, right? So pick a spot here, and I'm gonna walk it. I'm gonna go take this. So just to be clear, I have one point in the middle, and my other pencil is on the edge of the circle. Take it and now move it opposite. So make that point that is on the edge of the circle the center. And move it so you hit 2 spots of the circle. Here and there. You see that? So pick one spot on here using the same sort of radius. And again, my picture is not very good. Mark it off. So you have these 2 points right here and here on the circle. Do that again. So now let's take that point that we just made. And again, keeping the same radius, hit the circle here and there. So again, just keep going around, hitting every single time to that circle. All right, there. I'm going to keep doing that. You'll start to notice at some point that they start overlapping. There. And that should have overlapped there. When you're all done, do you all have 6 points that repeated? At some point, you can notice that it just keeps cycling back around. Somewhat 6 points. Stalling for general effect here. I hope the people that are remote are enjoying the pictures. We're like, well, now I want to find something. Quick, poke some holes in a piece of paper. All right, I'm going to connect my dots to make a hexagon. Hexagon has 1, 2, 3. I can do this. 4, 5. You guessed it, 6. Oh, that was awful. Okay, that's the best of my ability to make a hexagon. Fun fact, they knew, I don't know how much they knew, but at least ancient Greek mathematicians knew that when you do this, you will always make what is a regular hexagon. It has all the same length. These are all little equilateral triangles. For those, again, keeping track at home, here's a diameter right through the center. So what I'm looking at here, I'm going to do some math on the side, is they're assuming that maybe, just maybe, that hexagon is really close to the circle. Looks pretty close. Good enough. For practical purposes, maybe that's all they needed. I would also like to imagine, did you see how I did that when I was walking my compass? Maybe they did the same thing. When they made their radius with that piece of rope, the person who was standing at the edge of the circle just stayed there, and the other person moved to the circle. And then they just kept rotating back and forth around each other until they got back where they started. When they realized that they did that radius thing 1, 2, 3, 4, 5, 6 times, which is really what? 3 diameters. So the perimeter of this is 3 of the diameter of the circle. Just to make sure, the perimeter of the hexagon inside has 1, 2, 3, 4, 5, 6 of those radius, which is 3 of the diameter. So if I'm thinking that the circumference of the circle compared to its diameter is the same as the perimeter of the hexagon to the same diameter, well, then that must be 3 of those divided by that one. The ratio of the circumference to a diameter is 3. Close enough for pi. And for a long time, that's all they needed. Right? Again, I wasn't there. I don't know what they were doing. But in my mind, they were just making a rope walk along the circle. And then when they realized they can get back to where they started with doing that 6 times, they said, well, that's 3 times the length across. Hence, the ratio between the two must be 3. Magical. Right? So I think this is really cool. This is the kind of where I want to focus in my talk, that from way longer, this is what they had. This is how they understood things. They can construct stuff. They didn't even need numbers. I'm just noticing that the ratio of these two things is always 3. It doesn't matter how big it is, right? So even that early on, they knew that this was sort of a universal thing. It didn't matter what the actual diameter was. This always works. Cool. All right. So now I'm going to switch back and forth then. Let me go back to my presentation. So keep this image in your mind, right? You have this circle. You have a hexagon inside of it, right? And the inside one is 3. That's a good estimate. You can obviously see it's a little low, right? Pi is probably a little bit more than 3. Otherwise, we would be right on the circle. So, okay, yeah, maybe they knew that too. I don't know. Maybe they were okay with this. I have no idea. It wasn't there. All right, so moving on then. Let's go back to the presentation. So this is where they started, right? They had this ratio of 3. Boom. And then after that, at some point, again, this like pile of clay tablets at the end of the school year, they found another one. It's like, hey, turns out they knew that it wasn't perfect. Like that hexagon is not the whole circle. Right? So they kind of superimpose it on this like grid, maybe like a 5x5 grid, and said, well, the circle takes up the whole thing, but the hexagon only makes up like a portion of it, like 24 of the 25 pieces. So they made up this concept, this proportion that the ratio of the circle, their circumference, so C to P, the perimeter, is 25/24, right? The circle is, 25/24 the size of a hexagon. That was just their I don't know where necessarily other than this grid of squares. But putting that together with the 3 that they just found, if it's not a direct 1-to-1 relationship, then 25/24 of what they thought it was, which was 3, is probably a better estimate. And then we get this 125/24, which is 3.125, which is really, really close to pi for their purposes. I mean, it was good to the first decimal place. And just to be clear, I mean, I don't think anybody was disputing over the little bit of land lost over that disruption of pi. I would be surprised if they could tell the difference at that time. We can now because we're trying to get to like the moon, but still. But that's good. That's good. It's close. And like I said before, they're use base 60, and for other references, that's where we get the 60 seconds, minutes, 360 degrees in a circle. Oh, talking about circles. They knew 360 degrees, so we can use that too. And if you go back to the hexagon, thinking of splitting it up into 6 equal pieces, if anybody knows trig, 360 divided by 6 is 60 degrees. 60-degree angles have this awesome thing. It's an equilateral triangle, 60, 66. Oh, okay, cool. All these things fall out of that. I won't go there. But geometry really played into a lot of this. Okay, so that was the early years, starting out in Mesopotamia. Just real quick, an aside here, just so everybody's clear. Now that we have that concept of sort of splitting up the circle into these, like, we'll say triangles even, why am I focusing so much on the circumference? Because of this, right? So I'm only going to talk about the circumference because once we understand pi by the circumference of a circle, we can then translate that to the area, right? So here's a circle split up into, it doesn't matter how many wedges, but you take a whole bunch and you split one in half. And if we know that the ratio is, we'll call it pi, but whatever that number is, we know this is the circumference. So when I split this up and I rearrange them to look almost like a rectangle, it's kind of rectangular, you can see that the height here, this length, is just the radius, or half the diameter. And the length on either side will be half the circumference, right? You split the top half and the bottom half, and there they are. So if you multiply half the circumference times d over 2, or pi times d over 2 times d over 2, you get the formula for area. Done. So I don't need to work on determining the area based on pi. I can use the understanding of pi's relationship to the circumference, and then area just kind of comes from that. I love blowing people's minds. Okay, so there you go. So that's how we can think of the area of a circle from the circumference, right? From understanding those relationships. And again, this also goes to like, no wonder they're so impressed and surprised and excited about this relationship between the circumference and diameter. Look at all the usefulness of that. Let's keep going. And then, all right, some other ancient civilizations. We'll hit the 4 big ones at some point. So in Egypt, the Ames or Rhine papyrus, I have to take a moment, my cultural authenticity here. Ames was the Egyptian who wrote the scrolls. Rhine was some Scottish rich person who bought them. So I'm going to make sure I give credit to the Egyptian who actually wrote the papers, the papyri, not the person who bought them thousands of years later. So Ames in 1650, this like 16-foot long piece of papyrus rolled up, had hundreds of problems, and had tables and had graphs. But one of the problems that he puts out is he gives basically his formula for pi, or how to find the area of a circle, and it's 256 divided by 81. Right, 3.1605, which is pretty good. It's better than the one that we just had, but it's still not great. And this is the specific problem number 50. It says, cut off 1/9 of a diameter and construct a square upon the remainder. This has the same area as the circle. What? I would also like to point out, notice that they didn't really have symbols. They didn't have the same ideas that we did. So it was more rhetorical. Like, do this and you'll get the answer. Not 2 + 2 is 4. You know, if you add double the things, it's the words, right? Okay, fine. You want to see what's happening with that? Does anybody need to see the math here? Okay, so cutting off 1/9 of a diameter and constructing a square upon the remainder. All right, let's see if we can do this. My scrap paper. If I have a circle, let's just make this nice and simple so that everything works out. Let's say the radius is 1. That makes it real easy for us to do calculations. That makes the diameter, unfortunately, 2, but we'll come back to that. So if I take that diameter and I take 1/8 of it away, you got that? Taking 1/8 of it away. And then I square that. That's what it said, create the square from taking 1/8 away. That's like, so let's see, 1 minus 1/8, that's, oops. 1, yeah, sorry. So it should be 1/9, sorry. It was 1/9, thank you. So taking 1/9 away, we have 8/9 of 2 squared. All right? That is 4 times 8/9. But notice that the diameter here, or sorry, the radius of 1, what this amounts to then, and this is going to weird to see it, is I just lost my numbers. Sorry. It should be 64, 81st. I'm very sloppy with my writing here, and I already lost myself in the middle of this. Right, so now what we're looking at here is if I undo, I'm just going to subtract the 2 back from this, and I'll scroll back to my paper. So I lost track of my work. I'm just going to stop here in the short of this, but going back to what I had for my fraction, notice what we're doing here is saying, well, if I then take away the diameter from this, I get what their approximation of pi was, right? That ratio here, it's better. That 256 over 81, that was my 4, that's 64, that's squaring, right, over 81. And again, I didn't do it justice on this page because I didn't subtract the diameter at the end, but the way that they're working from this, when you cut off 1/9. And then again, I missed this picture here, but they have this grid of squares because they're always looking at areas as building squares, right? Squares, square meters, square cubits. That when you're looking at this grid of squares, they're thinking, okay, well, I'm thinking of a circle inside of this grid, and I'm excluding certain pieces of it from these squares. And then they flipped it and made it square again. And I'm not really doing justice in the explanation of this. Again, the point I'm trying to make is even in Egypt, they put geometry. They superimposed shapes over top of these things. And they said, well, if I make squares out of it, I can do this work, because they understood squares. Another classic problem from antiquity is this whole squaring of a circle. Can you do it? You can't, by the way, not constructing wise. All right, but sorry, I'll move on. So in Egypt, they had a slightly better approximation based on this idea of a grid of squares, and slightly better than the hexagon approach that we just looked at. It's referenced in the Bible, the number, the value of pi, in the building of Temple of Solomon, which was built in 960 BCE. So whenever written, that's when it was built. Here's the quote from 1 Kings, book 7. Anyway, he made a molten sea, 10 cubits from the one brim to the other. It was round all about, and its height was 5 cubits, and a line of 30 cubits did compass it. So if the diameter is 10 and 30 encompasses it, pi must have been 3. Makes everybody's catching that, right? If it's 10 cubits from one brim to the other, and it's 30 cubits encompassing it, that must have been a pi of 3. Now, okay, fine. This is where I just mentioned earlier about my love of history coming back, right, for some reason. When I was looking into this, interesting fact, there's still some contention about this. Some people are like, no, they had way better estimates of pi at that time. They would never have used 3. They must have been talking about from the diameter from the outside of one side to the outside of the other, but then the circumference is on the inside of it, right, because there's a width of it. Some people are like, well, it doesn't matter. It's just this giant cast brass pot. It doesn't have to be perfect, right? So maybe it wasn't a perfect shirt or something like that. Other people are noticing that in the Hebrew text, they added extra silent letters because of the way that numbers and letters correspond to each other in the Hebrew text. And if you take that extra silent letter as a proportion, the proportion to 3 gives you a value of about 3.1605, which was used at that time. So there's this idea that maybe underlying the Bible, that the Hebrew Kabbalah, the Jewish mysticism of numbers, is really secretly hiding what they knew about pi. Something I need to dig a little bit deeper in. But if anybody knows anything about religious studies or Hebrew text, I would love to chat with you about that one. That's something I'm like, maybe it wasn't 3 for them. Maybe it was something more, right? They added weird silent letters that they only did for mystical purposes. Maybe there's something to it, right? So Egypt had an idea, the Bible had its idea, which was really just referencing all the stuff that was happening at the time. And if anybody cares, is my fun picture of King Solomon's, the Temple of Solomon, a molten sea. It's really just a big bath for the priests as they went in. They just bathed outside in the hot water. Moving on. All right, so here's the big one, Archimedes. Right, so Archimedes comes in, and he's like, you know what? The Greeks have been working on proving lots and lots of things about geometry for a while. I think I got this. I think I got pi. I think we can figure it out. So in 287 to 212, that's when he was around, of Syracuse, so Greek, building off a work of previous Greek mathematicians. I want to make sure that that's clear. Antiphon and Bryson had already worked with this whole idea of inscribing shapes, like we just did. That's why I started the activity early, inscribing a hexagon inside of it. But then they went a step further and said, well, we knew that was an underestimate. If we bounce that and made something on the outside, do we get an overestimate? And then if we bound between that under and over, we'll get a better estimation of what we think pi is, right? They did it with areas, and this is called the method of exhaustion, by the way. They just said, we're just going to keep making these shapes until we, I'll say, get tired of doing it, right? And then it's close enough to a circle, move on, right? So we just did it with 6 sides. What if we went to 12, right? What if we went to 24? You double the number of sides each time, and you get better and better approximations, right? And they knew this. They could figure this out. What Archimedes really did is he took that theoretical leap and he said, we're not actually looking for the answer. We might never get there, right? He understood that this might be an unfindable thing, the way that we're doing it. But I can give you a better estimate, and I can even give you a method for finding a better estimate to it. So he used his same geometric methods. He literally compass and straight edge, marking angles, understanding how triangles work for ratios, and said, okay, I can approximate pi to between 223/71 and 22/7. If you take the average of those two, it's 3.1418. And if that doesn't sound impressive, look at the next thing. In order for him to have done that, he would have had to start with the 6 like we did and build up to 96 sides. And just to be clear, that's 96 sides inside and outside. So we made 2 shapes and measured the perimeter around both of those and said pi is between those 2 numbers. That is an impressive feat for 200, BCE, like whatever, over 2,000, almost 3,000 years ago. Wow. All right. So that's impressive. And again, they were actually kind of using the Babylonian number system, which was a hot mess. That's an even more impressive system. Okay. And because I'm this person, I do want to show you just real quick. Where is it? I have it here. My Archimedes approximation of pi. So it's really just, it's an applet. I didn't make it. but if you can hopefully see this. So we just did this one, down to 6. Our inside, right, we had a perimeter of 6, which was, twice of what we wanted, so pi was 3. If we drew one outside, which we could do, but we're not going to, we would find a perimeter of 6.92, which gives an approximation for pi of 3.46 something or other. Okay, just to be clear, going up, 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 up. This is what Archimedes did. And I'm sure he's looking at the same. I can't get it right. Same picture. Well, that's pretty much a circle. I'm not going to worry going much further, right? I think that looks pretty close to what the circle is, and you can't see it, but there's shading inside and out to make a 96-sided polygon. And there's our estimate, somewhere between these two numbers. Solid. All right, way to go, Archimedes. So much so that, well, I guess I'm not there now. So much so that later on we'll talk about how people just kept using that. They just kept doing that for years and years, thousands of years. Right? That's all that they had. Let's go elsewhere, and being mindful of timing, let's go there quickly. Right. So other contributions. So between 400 and 1500 CE, which is the sort of nature of history, everything moved from the Western world, so Greece and everything, and went east. So China is doing their thing. Zhu Gongxi in like 429, 501, somewhere around 500 CE, approximated pi by 355 1/13. 3.141592, and that's where he stops, 92, right? But everything up to that point, everything up to 1, 2, 3, 4, 5, 6 decimal places is good, right? And that's only like 200 years, 300 years after Archimedes. Oh, by the way, they didn't know each other. Zhu Gongxi, he came up with the same ideas of inside-outside shapes and sort of, bound them. This method of exhaustion was used there as well. But there's no evidence that they communicated. In fact, most of Greek texts weren't translated into Chinese until like 1200. So there's 600 years before any text really get translated. They knew, but I don't think they were communicating. In order for him to use Archimedes' method with that level of accuracy, he would have had to construct a 24,576-sided shape inside and outside. That is some crazy amount of dedication to a math problem, right? That's crazy, right? That's good for him. I don't know that I would have that dedication, but there it is, and they use that. That is the number that they were kicking around forever. Jumping a little bit, just trying to fit them on the page. In India, Madhava of Sangamagrama, shouldn't try to say it too fast, much later on, right? This is a different approach now, and I'm mixing it up a little bit. India was real big on their theoretical algebra stuff. They really pushed the algebra idea, the start of it at least. So they took away from the geometry and said, well, if we're just adding up things as we go and go and go, there might be a pattern. This could be what we call an infinite series. We're adding up a bunch of things. And one of the things that Madhava actually found out is that pi over 4 has this really interesting series, right? 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. You're alternating 1 over odd numbers plus or minus plus or minus. And he's like, yep, that's pi over 4. What? By the way, we still know that as pi over 4 today. We just have the ability to go a lot further into the sequence to find the answer. He stopped after 12 or 13 or 20 digits or increments, but you could get pi correct to 11 decimal places by doing this, right? A slightly different approach, not geometric anymore, but still the ideas from this sort of adding infinitely many things, and just sort of theoretically did it. This is also attributed later on to some European mathematicians, James Gregory and Gottfried Leibniz. Leibniz, if you know, was the calculus person, one of two. But they use the same method of infinite series. In the Islamic world, this is also happening sort of at the same time. China and India are doing their things. Al-Khwarizmi, the person we get the word algorithm from and the word algebra from, in 800 wrote this in his text, which has the word algebra in it. There's actually 3 estimations of pi in here, which I appreciate that they're like, yeah, use any one of them, it's fine. The first one is 3 1/7. So, and for every circle, when you multiply the diameter by 3 7/7, so 3 1/7 is the circumference that surrounds. So pi is 3 1/7. That's pretty close, actually. And it is a term among men that is unnecessary. And to those of geometry, there are 2 other sayings. The first one, multiply the diameter by itself, and then by 10, and then take the root of the result, and that is the circumference of the circle. An estimate for pi is the square root of 10. It's like 3.16 something. That's pretty close, too. It's not right, but square root of 10. Sure, why not? And then finally, the other used by astronomers, this is my all-time favorite from 800 CE, by the way, it's a long time ago. 62,832 divided by 20,000. That's pi. I have two questions for that. One, how? Right? And two, why? Especially after he says all of these are near to each other. It's like, no, that last one's actually really good. And I calculated it somewhere else. It's like 5 or 6 decimal places. It's pretty weird. And also I appreciate Al-Khwarizmi's approach to this. Like, for the every person, 3 1/7 is fine. For geometers, you might want to go something like square root of 10. For astronomers, like you want to go really far, use this really close number, right? And it's almost like acknowledging that we're never going to have the right answer, but at least we can say, like, for different purposes what we need. And then much later on, there's this huge gap. Al-Kashi, towards the end of sort of the before the Islamic world sort of fractured, got pi correct to 14 decimal places. Interesting. Al-Kashi actually used some of a mix of the geometry and infinite series stuff. Right? In Europe in the Middle Ages, just sort of a quick progression here. This is the late Middle Ages, so right before the Renaissance. Francois Viette from France got pi to 9 decimal places, which interestingly was less than what people in China and India had already figured out. They just didn't get it yet. Adrian van Roomen, a Flemish mathematician, pi was correct to 17 decimal places. This was an extension of all the Archimedes approaches. All of these people just came up with slightly different ways to do it that was more efficient. Ludolf van Keulen, pi to 35 decimal places. Such an amazing feat that even like in Germany for a long time, they called it the Ludolfi number. It wasn't pi. So if you look in German, like from way back, right, it's not pi, it's the Ludolfi number, right? He estimated to 35 decimal places. And these were all just the same approach, the same thing that we did where we constructed with the circle and the hexagon, that, and then he measured the sides based on the proportions. Then to today, right, there's the boom, 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 things start to happen, right? So after the Renaissance, Gottfried Leibniz and James Gregory, they had that infinite series approximation. They actually refined it. They made better approximations so that things that they didn't have to add up as many terms to get a better approximation. The one that was used in India was very slow to get to a good answer. So this is around the 17th century. And then, I won't go through all this, Sharp gets 71 correct. Maction makes some improvements and gets 100 digits, and then it's 112, 136, 440, and it goes all the way to 77. I appreciate this. In 1873, a mathematician by the name of Shanks calculated 707 places. Unfortunately, it wasn't until many years later that we realized he was only right up to the 528th one. And then someone's like, everything after that was wrong. But yeah, you're doing math by hands and it takes you like months to do it, you're going to make a mistake. And if you're doing months worth of work, people probably aren't checking it too rigorously. So for years, that was fine. Okay, but I mean, even 527 digits is good. Still more than the previous one. The actual symbol that we use for pi, the Greek letter P, was used by William Jones in 1706, popularized by Leonard Euler, famous mathematician, just wrote it everywhere and said, use it. Other people used it, but not in the same context. And then two sort of little things here. Pi was proven to be irrational in 1761. We kind of had a suspicion that we couldn't write it as a fraction, but now we know. It's also transcendental. In 1882, Lindemann figured this out. Basically, what that means is if I have an equation with a polynomial, like, you know, powers and multiples with rational exponents or coefficients, pi will never be a solution. Pi is not a solution to any sort of algebraic polynomial. Good to know. I won't go into that proof, but it's there. This is what happened. Something a little different. I think this was also interesting. I pulled this one out. George Buffon calculated pi based on probability. And really, he used pi in a probability thing. And this is a fun. If you drop a needle on a page with lines a needle length apart, so I think you have parallel lines on a page and they're the same length as a needle. If you drop a bunch of needles onto it, the proportion, the probability that you land on a line is 2 over pi. And there's a whole bunch of that is true. So really, if you want a simulation, just drop a bunch of needles onto a thing and do the calculation yourself, right? And what you'll do is you figure out how many you dropped, divide that by how many actually hit, multiply it by 2, there's pi. Close enough. Maybe. Let's find out. Another simulation, right? So I'm just going to drop 1,000 things. There's a bunch of, here they are. And luckily, the simulation tells me 3.115. That's pretty close. Let's see if we can get closer. 3.147, closer. Nope. Right, so you see, again, the idea with probabilities is in the long run, eventually, when you do this an infinite amount of time, that number should get closer. So that's an interesting thing. Don't use this as an estimate of pi. Please do not simulate pi. That's not how this works. But it is an interesting thing. I'm sorry, my screen's weird. There it is. That's better. So it is an interesting thing that this works. This is, I mean, theoretically it should. So Buffon's, that's not great. I mean, please don't take what Warren said. We can estimate pi by dropping needles. That's not what I'm saying, but it's an interesting thing. All right. So here. All right. So yeah. So that's him. Also, moving into modern days. So computers started in the 40s, right? Started. So ever since then, it's like, oh, just put it in the computer, right? The big push now is let's come up with a better algorithm for calculating pi. We already know how to do it. We just have to like sit there and wait for it to happen. So algorithms started calculating pi, and they're actually used. They were used to test processing speed. You know, a new processor. Like we know how long it takes a computer to do this calculation, right? And then we could test the speed of it. In 1945, D.F. Ferguson found 808 digits of pi. It took about a year. 4 years later, 2,000 digits of pi in under 3 days. That's pretty quick. I mean, we can think of like the evolution of computing by how fast did it take to compute pi. That's fast. That's some progress. And this is all based off of the work of another Indian mathematician, Ramanujan, what he did is he took those sequences that were building up and he found really, really quick, really good, efficient ones. So quickly converging means you had to even have to add up too many numbers before you got a really good approximation. And just to freak people out, I threw one in there. There it is. Right, so that's his formula for 1 over pi. Ew. Some fun facts. Let's end with some fun facts. Right? Pi is used for finite answers to infinite sums. If we're finding pi through infinite sums, then maybe it works backwards. Here's another interesting formula. If you add up the reciprocals of squares, so 1 over 1, 1 over 4, 1 over 9, 1 over 16, if you add them all up, you get pi squared over 6. What? But it's cool, you did, right? And that's like, okay, that I could see, like, I could actually maybe come up with an example of where I might need to add reciprocals of squares. And you're telling me pi squared over 6? Yes, I am. Yes, I am. It contains all the digits, so 0 through 9, and theoretically an infinite number of times, right? It's random. It's actually been proven that the numbers show up randomly. It's not, I mean, they're based on the pi, but it's interesting though. Okay, so all of them. March 14th, which is Pi Day, 1879, is Albert Einstein's birthday. Coincidence? Maybe. I think not. But yeah, that's a fun fact. In 1897, this is so funny, Indiana tried to pass a law making pi equal to 3.2. It got halfway there. The House is like, yeah, that sounds great. Senate's like, you're an idiot. So yeah, we were very close. Indiana was very close to having 3.2 being pi. And they did that for like, and there's a really funny story. Like the guy that came up with his proof as to why it was 3.2 was very like confident in his answer, and he like copyrighted it. So in order for the state to use it, he had to like give them permission to use his formula without charging them money because he had a copyright. He was completely wrong. Just want to make sure we're all clear that it's not 3.2, and his proof was really bad, but no one challenged him. So there you go. On the other side of that, the really good pi stuff, in 2015, Suresh Kumar Sharma, who was a vegetable vendor, right? He's worked in a market, pi to 17,000 digits. Recited, blindfolded. Took him 17 hours to recite pi. Just to be clear, it took longer than that for the computer to calculate it first. But notice, 17,000 digits, that's a lot. That's a lot of time. That's crazy. And just to put it into perspective, we actually only need 15 digits of pi to get to another planet accurately. Like any planet that we can see in our solar system to get there, we only need 15 digits of pi to get there accurately. So all of these estimations beyond that were purely academic. Even better, 39 digits of pi is all you need to calculate the size of the universe, to within the size of the nucleus of a hydrogen atom. And we're calculating it to, where are we now? Oops, we are at, I lost my thing. Where is it? There it is, sorry. 22.4 trillion digits is how many we've calculated from computers. We only needed 39, but we're still going. We're still doing it. Right, and so I am aware of the sort of rapidly approaching time here. So I'm just going to sort of abruptly end with the whole pi started out from this, I need to understand this so I can create a circle. The only way I understand things like this is through construction, through actual practical building of things, maybe pulling ropes along. But then from that, we said, well, I can abstract that. I can draw better pictures. And then we start to abstract it, and then the world explodes with all this theoretical knowledge. And it's like, let's forget where it came from in the geometric sense and see how it evolved and where it goes. So now here we are in this new world of technology, and we're like, it's almost becomes purely academic, but we're looking for patterns in pi. We're looking for things that we didn't think were even possible to like see in the first place, but we're seeing them, we're looking for them. Just for the fact no one's found anything fun in pi yet. But we're looking, and now that we have so many digits to look at, let's see what happens. I know that I didn't dig too deep into some of the math, and that was deliberate. If anybody does have any follow-up or any questions at all, please let me know. Here I am. I'm Professor Warren Sides. You can send me an email, sides@champlain.edu. And if anybody wants any of these sort of resources, I am recording, obviously, so that will be shared at some point too.